Okay, here is question number 2 of the 2019 AP Calculus AB exam. This was not on the BC. This is a calculator question. I have not read the question yet, so I'm solving this in real time. Hopefully I don't embarrass myself. Okay, so we have a table. Meters gives us a velocity of particle P moving along the x-axis. They tell you that V is differentiable. VP, what is P? Particle P. Okay, I guess they're going to introduce a particle Q. Yep, there it is. Particle Q's in question C and D. Okay, V is measured in meters per hour. Select values of V are given in the table. P is at the origin at time 0, so I'm going to make a note to myself that my x coordinate of particle P at time 0 is 0. That's an initial condition. They'll probably ask us to find or estimate a position later on. Let's see, justify why there must be at least one time on 0. I'm sorry, from 0.3 to 2.8, at which v prime of t, the acceleration of the particle, equals 0 meters per hour per hour. Okay, anytime you're trying to guarantee the value of a derivative, you are going to start with the mean value theorem. In this case, we are looking for the derivative of this function to equal 0, which is also Rolle's theorem. So this is going to be a mean value theorem / Rolle's theorem approach. Okay, and first, if you're going to use mean value theorem or Rolle's theorem, I'm going to reiterate that the velocity is differentiable. So Vp of t is differentiable. That's given to us in the paragraph, but I feel better if I write that because that is the condition that allows you to use the mean value theorem. So we're differentiable on the interval 0 to 4, which includes 0.3 to 2.8, which is what we're interested in. We want the acceleration to equal 0, and that's going to happen because my particle has a velocity of 55 meters per hour at 0.3, and my velocity my velocity at 2.8 is also 55. So since Vp of 0.3 is equal to Vp of 2.8, and they both equal 55, Rolle's theorem, or you could say mean value theorem, Rolle's / mean value theorem guarantees, that says since. My since looks like garbage. There. Guarantees that the derivative of velocity must equal 0 for some t. We don't know where, but we do know that it happens somewhere on the interval 0.3 to 2.8. So that is a Rolle's theorem question. Question B, use a trapezoidal sum with the subintervals indicated to approximate the value of 0 to 2.8, 0 to 2.8 of V of P of t, and this is an approximation, so you need to make sure you put an approximate symbol right there. And if we're going to do trapezoids, we have to do 3 separate trapezoids, so that's going to be 1/2. The height of the first trapezoid, if we're going from 0 to 0.3, is going to be 0.3, and the sum of the bases would be 0 plus 55. My next trapezoid goes from 0.3 to 1.7. That is a distance of 1.4. And the sum of the bases of that trapezoid would be 55 minus 29. So we have a value of negative 29. And then 17 to 2.8, that is a distance of 1.1. So the height of that trapezoid is 1.1, and the sum of the bases would be negative 29 and 55. And I'll throw that in the calculator to get an answer. Let's see, now I forgot what it was. Oh, shoot. So it's half of 0.3 times 55, so half of 0.3 times 55 plus half of, it was 1.4, and 55 minus 29 plus half of, and then it was 1.1, and negative 29 plus 55. Enter, and we get 40.75. All right. C, A second particle also moves along the x-axis so that its velocity is given by this. So we have a velocity of a particle q is given by that function. And I'm just going to make a note. I'm about to plug this into F1 in just a minute. Find the time interval at which the velocity is at least 60 miles per hour. So we want the velocity of particle q to be at least, which means it must be greater than or equal to 60, and we will solve that graphically. I will graph the function y equals 60 in F2. Find the distance traveled on that interval. So the distance traveled would be the absolute value, the area under the absolute value of that from when we'll find the two time intervals. So I'm going to go to my calculator now, and that function, whoops, is 45 times the square root of x times the cosine of 0.063 x squared. Make sure I got all that in correctly. 45 roots x cosine 0.063 x squared. Good. And then I'm also going to, oh, come on. There it is. Okay. I'm also going to graph y equals 60, which is way off my screen, so I'm going to go menu, analyze. Do they give us a time interval? Only on 0 to 4. Okay. So let's go window, settings. My x's are 0 to 4, and my y's, I'll just go 0 to 100. I want to make sure I get 60 in there somewhere. And now I can see where my function is above the line y equals 60. I need those intersections. So analyze, intersection. There's one. Menu, analyze, intersection. There's the other. I'm going to store those. Control store for A. Control store for B. And so that, my velocity is above 60 on 1.866. That says less than equal to. Less than equal to t. Less than equal to 3.519. And those are my limits of integration right here. All right, so now I'm going to go to my compute screen, whoops, and I will do the antiderivative from A to B. And you do want to store those values because that guarantees accuracy of the absolute value of f1 of x. Tab dx. Control to force the decimal, and we get 106.1087. And that distance would be measured in meters. The only thing I wish they would have done in this question is say total distance instead of just distance, because for a second I was debating whether we should do displacement versus total distance. A displacement question, you just drop the absolute values. I do think that they are wanting total distance here. So last part, at time 0, particle q is at position negative 90. Okay, so my particle q at time 0 is at negative 90. Use the result from part B and the function v of q to approximate the distance between the particles at time 2.8. So I need to know both of their positions at 2.8. So my position of q at 2.8 is going to be its initial position plus the area from 2.8. Nope. Yep. What am I doing? No, I'm sorry. From 0 to 2.8 of the velocity of q, which I have stored in my calculator as f1. So I'm going to go to my calculator here, and whoops, that's not what I wanted. Negative 90 plus shift plus 0 to 2.8 of f1 of x. dx, control enter. And I get 45.9376. Okay, I did get a little exclamation point there. I want to see what that's about. Result obtained using approximate arithmetic. Okay, so it uses some kind of area approximation technique because this antiderivative is not one that can be done easily. So it probably used like a Riemann sum with 2 billion subintervals. I don't know. Okay, so I now need to know where my particle P is. So my position of particle P at 2.8, same setup, is going to be my position at particle P at time 0 plus the area from 0 to 2.8 of the velocity of particle P. And the initial position of P, I wrote this way up here, it was 0. And so I think I'll just take this out and write 0 there. And the area under V of P was approximately, we did this with the trapezoidal approximation up here, 40.75. And so the distance between them would be 45.9376 minus 40.75, and that answer is, whoops, we're going to do that answer minus 45 point, and I just forgot what it was, 40.75. Well, I was way off. 40.75, enter, and they are 5.18, approximately 5.1876 units apart. Use the result to approximate the distance, and there we go. That would be in meters apart. All right, there we are, and there is all of part of question 2 from the 2019 AP Calculus exam. 11 minutes.